Here is an example of a complex motion. Um, so let's write here, this is a complex motion. And these graphs are the most used graphs in my tests and exams, all right? So I make sure you get comfortable with these type of graphs, with velocity time graphs. So the requirement here is to describe the motion and to produce the other motion graphs. We're going to sketch them. And it says here, let west be positive. All right. So first, let's describe the motion. Okay. In order to describe it, since it's a complex motion, as you can see, the acceleration is not constant, right? Is not constant. So what we have to do is we have to divide in sections where the acceleration is constant. And that case is going to be easy for us to analyze it. And I'm sure that as soon as you see those, you saw this graph, and I put this as a requirement, you already have in your mind your sections, and here they are. The first one is the first 2 seconds, then the next 2 seconds, then the next 2 seconds, and then the last. All right, so the total time is 8 seconds. So here is 1, 2, 3, and 4. So I divide into 4 sections. So for some of you, the only confusion may have been, why did I split into the 3 and 4, the last part, even though the acceleration is uniform? Because at this point here, there is a change in direction. Right. So in the position time graph, there is going to be a change in curvature. All right. So let's start now describing it. Okay. So on the first part, it's a uniform accelerated motion. Right. It's moving west on the positive direction and is speeding up. What do we know about initial velocity? Well, it's 0. The final velocity for this part, vi is 0, and vf is plus 20 meters per second. All right. The time is 2 seconds. Okay. Can we find the? Actually, let's not focus on the numbers. Let's keep moving with a description only. So if you don't mind, I'm going to erase this, and we'll do that separately so we don't get confused. All right. Part 2. Well, part 2, as you can see, the velocity does not change, so it's uniform motion. However, it's still traveling westward, and the speed is not changing, right? Part 3, it's a uniform accelerated motion. Remember, it's still traveling west. It hasn't crossed the time axis yet. However, it's not speeding up, but it's slowing down, right? And lastly, part 4, it's uniform accelerated motion. Why is it uniform accelerated motion again? Because the velocity time graph is a straight line, slanted one, okay? However, now it's traveling the negative direction, right, which is east, and it's not slowing down, but is speeding up, right? The velocity goes from 0 to 20 meters per second east at the end of the 8 seconds. All right, so we are good with the description. Now let's start finding some numbers before we graph, right? Let's find some quantities. So let's start with how long did all the travel take? Well, it took 8 seconds, right? Let's find now all the displacements for each section, right? So delta d1 for the first 2 seconds, remember, is the area under the graph, between the graph and the time axis, which is just that one there, and it's above the time axis. So it's a triangle, base times height divided by 2. So 20 times 2 is 40, divided by 2 is 20, so it's plus 20 meters, right? You travel 20 meters west. Delta D2, it's again the area under the velocity time graph and the time axis. And it's a constant one, so it's a rectangle. So it's 20 times 2 is 40 meters, right? Then we can find delta D3, which is now this area here. Right? Which is the same as the previous one, as 1, but now it's negative, right? Because it's traveling. So it's still positive. My apologies. It's above the time axis. So it's 20 times 2 divided by 2 is 20 meters. So as you can see, in total, delta D, let's call this west, is actually 80 meters. Right? So this object has traveled 80 meters west. Then it stopped at 6 seconds. So at t equal to 6 seconds is at rest for that brief moment. And then it switches direction, right? So now we have to find this area here. All right, and that is the only displacement on the opposite direction. All right, so delta D4 is negative 20 meters, right? So delta D east, only one E is enough, is equal to negative 20 meters. All right, so what is delta D total? Well, it's a sum, right? Delta D1 plus delta D2 plus delta D3 plus delta D4. So delta D total is actually 60 meters or 60 meters west. What is the total distance traveled? Well, in this case, we actually just add all the magnitudes of each displacement, because this object, it did travel all the distance regardless of the change in direction, right? So it's 80 plus 20 is 100 meters. So now can I find average velocity? Absolutely yes. Average velocity is delta D total over delta T. So average velocity is 60 divided by 8. So it's plus 60 meters divided by 8 seconds. I'm just opening my calculator. 60 divided by 8 is 7.5. So average velocity is plus 7.5 meters per second. Can I find average speed? Yes, I can. It's total distance over time. So average speed is 100 meters divided by 8 seconds. So remember, this is a scalar quantity, so I don't care about directions. And that is 12.5 meters per second. All right. Can I find the acceleration on each section? And all we have to do is find the slope, right, of the velocity time graph. And as you can see, the first one is 10, 0, and negative 10, right? So the acceleration for the first part is the slope, which is plus 10 meters per second squared. The acceleration in the second part is 0 because it's horizontal, and the 3 and the 4 are the same. It's a slope of the whole line, which is negative 10 meters per second squared. All right. So now we are ready to produce the graphs. We got all information, so quantitatively we found everything. Now we're just going to sketch DT and AT graphs. All right, so let's do that. So let's start with position time graph. Remember, west is positive, so I'm gonna as always say 1 2 3 4 5 6 7 8. This is 10 seconds, and the time that we care are 2 4 6 and 8. And usually what I do is I draw some dashed lines, so I know that these are going to be different sections. Remember those sections 1 2 3 and 4. All right. I don't know initial position, so I'm going to assume di to have a value. Usually the easiest one to be 0, right? So what happened on the first 2 seconds? Remember, the object was uniformly accelerating on the west direction. It traveled at 20 meters, all right? So I put here 20, and then it traveled another 40, so 60, and then another 20, so 80, right? And then it went back. So this is the highest, the furthest that it traveled west, right? And then it came back. So what we do here is, what do I mean by sketching? We just draw the shape in general, how it looked like. We don't worry about too much about the curvature. So the first 2 seconds, it traveled 20 meters, and it sped up, right? So it's going to be a curve, a parabola opening up, right? And it starts from rest. Then it traveled at, I'm going to do them in different colors just so that we understand the different parts. It traveled at constant velocity west for 40 meters. Then it traveled another 20 meters still west, but slowing down and eventually stopping, right? And then it switched direction. It traveled east another 20 meters, speeding up, right? There is your position time graph. This is what I mean by sketching. What you did is, so what is important is for a sketch are the key points and shape. Of the graph. All right. And if you've done them, then this is good for getting 100% on your test. So now let's do the acceleration. The acceleration is very straightforward, very simple. Okay, please make sure that you all get the marks for that. So usually what I do is I do the same thing. I divide into, once I label it, I divide into sections. Now it's acceleration, and it's meters per second squared, and positive is west. All right. So we had two values. If you remember, we had either 10 or negative 10. Okay, so I'm going to use a different color here. The first 2 seconds, it was plus 10. Then it was 0. And then the last 4 seconds, it was negative 10. All right. And here is your acceleration time graph. That's always how it's going to look like in grade 12. A step like graph, okay? So horizontal lines only. If you have any slanted line, it means you've done something wrong. This is a complicated example, and something like this, you'll have it on your unit test. So make sure you review this video and you practice. You get a velocity time graph and try to do it. All right.